Between two dying galaxies, something impossible is being born. A black hole 1,000,000 times the mass of our Sun appeared, where no black hole should exist. It floats in the void between colliding worlds, feeding on a glowing bridge of hydrogen gas. We thought black holes needed billions of years to grow this massive. We were wrong. The James Webb Space Telescope just found evidence of direct collapse, a cosmic shortcut that breaks every rule. What it discovered changes everything. Two galaxies are tearing each other apart billions of light years from Earth. Their death dance created something astronomers had never seen before. When researchers Pieta van Dam and Gabriel Bremer were scanning archived images from the James Webb Space Telescope, they froze. There on their screens sat a shape that should not exist in nature. A perfect figure 8, an infinity symbol blazing in the cosmic dark. The image showed two brilliant red cores, each wrapped in glowing rings of stars. They mirrored each other like cosmic twins frozen in time. Between them stretched a bridge of bright green light hydrogen gas, stripped to its bare atomic bones. Scientists confirmed it formed when two massive spiral galaxies slammed into each other head-on. The collision was so violent it reshaped everything. That green bridge of gas was glowing for a reason. Something in the middle was eating it, something that was not supposed to be there. The two galaxies collided with such force that their stars flung outward into rings, while their gas clouds smashed together in the center. It was like two water balloons hitting each other at high speed. The rubber flew apart, but the water crashed together in a single explosive burst. Except this water was 1,000,000,000,000 times the mass of our Sun, and the explosion was still happening. Webb's infrared camera could see through the cosmic dust that hides these collisions from ordinary telescopes. The twin red cores glowed because they were packed with older stars. The rings shone with new blue stars born from chaos. The green glow came from hydrogen being ripped apart by something with immense gravity. The team nicknamed it the Infinity Galaxy, not just for its shape but because it might have created something that can never be. Destroyed a black hole. Galaxy collisions happen throughout the universe, but this one revealed a recipe scientists had been searching for. The exact conditions to birth a monster. When the team looked closer at that glowing bridge, they found signatures of intense radiation, X-rays, radio waves, the unmistakable signs of a supermassive black hole actively feeding. But supermassive black holes live at the centers of galaxies. They anchor everything around them. This one was floating in between. That triggered an immediate puzzle. How could a black hole weighing 1,000,000 suns end up in the middle of nowhere? Did it get ejected during the collision? Did it wander in? Or did something stranger happen? To find out, they needed to prove the black hole really did not belong there. Black holes do not drift through space like tumbleweeds. Every major galaxy ever studied has one at its heart. The Milky Way has Sagittarius A, about 4,000,000 times the Sun's mass. Andromeda's is even larger. They are galactic anchors, not wanderers. So when Van Dam's team confirmed a supermassive black hole sitting between the two cores of the Infinity Galaxy, the astronomy community erupted with questions. This was not a small stellar black hole. It was a giant that should have been locked in place by billions of stars. The black hole sat exactly in the middle of that hydrogen bridge, not near either galaxy, but dead center, as if placed there on purpose. They measured its position repeatedly. Every measurement confirmed the same impossible fact. 3 explanations emerged. Perhaps the black hole had been kicked out from one galaxy during the crash. That can happen when galaxies merge, and their central black holes spiral together, throwing each other around like cosmic wrestlers. But an ejected black hole would be moving at thousands of miles per second, racing away like a bullet. This one was not moving fast. The second idea was a cosmic illusion. Maybe a third galaxy sat directly behind the collision from our perspective. Its central black hole could appear to lie between the two galaxies, though it was actually far away. Astronomers call that a chance superposition. The third idea was the one that changed everything. What if the black hole had formed right there in the gas bridge during the collision itself? That would violate everything in the textbooks. Black holes form from dying stars, not from clouds of gas. But there had long been a whispered theory suggesting that under perfect conditions, a massive gas cloud could skip the star phase entirely and collapse straight into a black hole. Scientists called it direct collapse. It had never been seen. Until now it was only theory. The team knew they needed proof. They had to measure how fast the black hole was moving compared to the gas around it. If it raced through space, the ejection theory would win. If it sat still embedded in the gas like a spider in its web, then something revolutionary had occurred. While waiting for telescope time, they calculated how massive this thing really was. The number shocked them. 1 million suns compressed into a space smaller than our solar system. They double-checked with multiple methods. Every result came back the same. To understand how absurd that was, they compared it to normal growth. A typical stellar black hole weighs maybe 10 to 100 times the sun. That is the seed. From there it grows slowly by feeding on gas and dust over billions of years. There is even a limit called the Eddington limit that defines how fast a black hole can grow because the radiation from infalling matter pushes back against new material. Even feeding at maximum speed, constantly a 10 solar mass black hole would need billions of years to reach 1 million solar masses. But the James Webb Telescope kept finding supermassive black holes in the early universe less than 1 billion years after the Big Bang. The math did not work. The Infinity Galaxy black hole was one of these impossible objects. Its size fit perfectly into the range predicted by the direct collapse theory. Born big, born fast, but weight alone was not proof. The team turned to the glowing gas surrounding the black hole. That green light was more than beautiful, it was evidence. Hydrogen gas becomes visible to Webb's instruments only when blasted by extreme energy. The glow showed where radiation from the feeding black hole was ripping electrons from atoms. As the atoms recombined, they emitted light. The pattern of the glow mapped the reach of the radiation like a crime scene photograph. X-ray and radio telescopes confirmed the same location. 3 independent observatories all pointed to the same spot. Something huge was eating in the middle of the bridge. The ionized gas let them measure movement too. Light from gas moving toward us shifts slightly blue. Light from gas moving away shifts red. By measuring those shifts, they saw turbulence, chaos, and swirling motion through the entire bridge. Shock waves rippled through it. This chaos would soon become the key to understanding what happened. For decades, scientists believed they understood black hole growth. Stars die, black holes are born. Those black holes merge and grow slowly. This is the light seed theory. But the light seed path cannot explain the monsters Webb keeps finding near the dawn of time. Even under ideal conditions, a black hole starting at 10 solar masses could never reach 1 billion solar masses in 500 million years. It is like finding a full-grown tree in a forest planted yesterday. Something else had to be happening. Some scientists proposed that under special conditions, gas clouds could collapse directly into massive black holes without forming stars first. These would be heavy seeds between 100,000 and 1 million solar masses at birth. If such seeds existed, they could grow into the giants we see. The math works if you start big enough. But until the Infinity Galaxy, there was no evidence that direct collapse ever actually happened. The key to direct collapse is preventing star formation. Normally, gas clouds fragment into countless small clumps, each becoming a star. To make a single black hole, the gas must stay unified. That requires keeping it hot and turbulent, so it cannot cool and fragment. In the early universe, ultraviolet radiation from nearby young galaxies could destroy molecular hydrogen, the main coolant in gas clouds. Without that coolant, the gas stayed hot and collapsed as one mass. But that could only happen when the universe was young and pure, before heavier elements spread everywhere. Later, gas became contaminated with metals which cooled it easily. Direct collapse should have been impossible in modern times. Yet the Infinity Galaxy proved otherwise. The 2 colliding galaxies created extreme turbulence. Their gas clouds smashed together at hundreds of thousands of miles per hour. Shock waves compressed the gas to immense density and heated it to millions of degrees. Normally, that would trigger intense star formation, but the turbulence constantly stirred and reheated the gas, preventing it from settling into stable star-forming clumps. High pressure kept it from fragmenting. Instead, the whole bridge began collapsing under its own weight. Gravity and turbulence fought for control until gravity won. The center of the gas bridge reached densities and temperatures where nothing could stop the collapse. Within a brief cosmic moment, an event horizon formed. A black hole was born between the galaxies. The conditions mirrored those of the early universe, but through a different mechanism. There was no pristine primordial gas here, no ultraviolet radiation breaking molecules apart. Instead, turbulence itself prevented star formation and maintained high temperatures. The result was the same: a massive black hole formed in one catastrophic event. Gas continued to funnel inward, feeding the new black hole. The process happened incredibly fast by cosmic standards, perhaps. Within a few years from start to finish. When Webb and other telescopes observed the region billions of years later, the newborn black hole was still young and active. It was surrounded by an accretion disk glowing with X-rays and radio waves. The surrounding hydrogen bridge stretched for thousands of light years, illuminated by its radiation. The team knew that to confirm the direct collapse theory beyond doubt, they needed one critical number: the velocity of the black hole itself. If it matched the gas motion, it must have formed there. If it differed significantly, it must have been ejected from elsewhere. They applied for more observation time. Webb's spectrograph split the light into detailed spectra, showing the Doppler shifts of different gases. Gas near one galaxy core moved toward us at about 270 kilometers per second. Gas near the other moved away at 290. Then came the black hole's measurement. The gas immediately surrounding it moved at 280 kilometers per second, right between the two values, matching the local gas within 10 kilometers per second. That meant it was not racing through space, but moving together with the gas. It was born from that gas. The ejection and background galaxy theories were eliminated. The velocity match supported direct collapse. This measurement became famous as the 30 kilometer per second rule. If a black hole's velocity matches the gas around it within 30 kilometers per second, it likely formed in place. Anything beyond that suggests ejection or projection. The infinity galaxy black holes match within 10 kilometers per second fit perfectly. But the surprises did not end there. Further analysis revealed not one but 3 active black holes in the system. Each galaxy core contained its own supermassive black hole still feeding. And between them sat the newly born one in the bridge. 3 in one system, a cosmic rarity. The 2 older black holes each weighed about 10 million suns, while the central one was only about 1 million. Together they formed a natural laboratory for studying how black holes interact. Over millions of years, the 2 galaxy cores will merge completely, and their central black holes will spiral together, emitting gravitational waves before merging into a single larger one. The fate of the third younger black hole is uncertain. It might merge later, or be flung into intergalactic space by gravitational forces. The discovery reshaped our understanding of cosmic evolution. It suggested that direct collapse is not confined to the early universe, but can occur whenever conditions align violently enough. Galaxy collisions may regularly create heavy seed black holes that later become the giants anchoring galaxies. The infinity galaxy may simply be the first time humanity has caught the process in action. Detecting and confirming those black holes was not easy. By definition, black holes emit no light, so scientists had to rely on the evidence left behind by their feeding. The Chandra X-ray Observatory saw intense radiation coming from 3 distinct points. Each one matched perfectly with the infrared and radio data from Webb and the Very Large Array in New Mexico. X-rays revealed gas heated to millions of degrees as it spiraled toward oblivion. Radio signals came from jets of particles blasting out at nearly the speed of light. The spectral fingerprints were unmistakable. All 3 sources were actively accreting matter, converting falling gas into radiation. The middle source was weaker and younger, matching the estimated 1 million solar mass object, while the 2 older black holes at the galaxy cores were 10 times heavier and steadier. The system had become a cosmic triad, a perfect natural laboratory. The formation of this middle black hole might have solved one of astronomy's most persistent mysteries, but it also created new ones. If direct collapse can occur during violent galaxy collisions even in the modern universe, then heavy seeds might form far more often than expected. That would mean galaxies could be building new supermassive black holes continuously, rather than relying only on relics from the early cosmos. The cycle of creation and destruction could be repeating right now in thousands of colliding systems across space. The infinity galaxy might not be an exception, but a revelation of an ongoing process the universe kept hidden until Webb's vision exposed it. To understand how rare that event really is, scientists simulated similar galaxy collisions using supercomputers. Most scenarios did not produce conditions extreme enough to trigger direct collapse. Star formation usually wins, but when two large spirals collide head-on with perfect alignment, shock waves and turbulence can reach the critical threshold where gas cannot fragment. That combination is rare but not unique. Observational surveys suggest a few such perfect collisions may occur somewhere in the visible universe every few thousand years. Each could give birth to a new massive black hole between galaxies. If this mechanism repeats over billions of years, it might explain why we find so many supermassive black holes scattered across cosmic history without requiring all of them to form in the first billion. Years after the Big Bang, the infinity galaxy also gave scientists a way to test how turbulence controls cosmic evolution. Turbulence is chaotic motion of gas that injects energy at all scales, from giant eddies spanning thousands of light-years down to microscopic whirls. In the collision bridge, the turbulence was supersonic. Gas streams crashed into one another at speeds 5 to 10 times faster than sound. That constant chaos kept the temperature above 10,000 degrees, preventing cooling. It also balanced gravity in a delicate struggle. On small scales, turbulence ripped forming clumps apart, halting star formation. On large scales, gravity kept the whole bridge contracting. The balance between these forces determined the final outcome. When gravity finally won in the center, collapse became unstoppable. The event horizon formed in less than a year, transforming a massive gas core into a black hole almost instantly on astronomical timescales. This was not the gentle birth of a star, but a catastrophic implosion of a cloud millions of times more massive. The process likely passed through a brief stage called a quasi-star, an enormous bloated object where a dense core was trapped inside an envelope of infalling gas. Inside, pressure and temperature built until neutrino cooling triggered runaway collapse. Within hours, the core collapsed to infinite density while the envelope continued falling in. That material fed the newborn black hole at rates far beyond the Eddington limit until radiation from the accretion disk blew the remaining gas away. When the dust cleared, a 1 million solar mass black hole stood between two galaxies. The young black hole's behavior provided even more confirmation. Its X-ray and radioluminosities matched theoretical predictions for an object of that mass accreting at near maximal rates. The size of the ionized hydrogen region around it also fit perfectly with models of heavy seed growth. It was as though the universe had staged a laboratory experiment to show humanity how supermassive black holes can be born. Scientists now had the missing link connecting the tiny remnants of dead stars to the colossal engines that power quasars and shape galaxies. The implications stretch far beyond one discovery. If direct collapse can occur through turbulence rather than radiation, it means the recipe for heavy seeds is simpler than previously thought. Any environment that compresses gas enough and prevents star formation might produce them. That includes galaxy collisions, dense clusters, or even extreme regions inside giant star-forming nebulae. The boundaries of where and when black holes can form suddenly expanded. The universe may be constantly creating them in ways we never imagined. For astronomers, the infinity galaxy became a treasure trove of measurable data. Its light had traveled billions of years to reach Webb's sensors, carrying encoded information about the conditions at the time of collapse. Every photon from that glowing green bridge told part of the story. The ratio of emission lines revealed gas density. The spread of wavelengths revealed velocity dispersion. The alignment of polarization vectors mapped magnetic fields. Together, these details painted a vivid picture of the cosmic storm that birthed the black hole. Even more astonishing was the fact that the triple system seemed dynamically stable. Despite gravitational attraction among three massive objects, they had not yet merged or flung one another away. Computer models suggest they are locked in a slow orbital dance that will last tens of millions of years. Eventually, gravitational radiation will drain energy from the system, causing the black holes to spiral together. When they finally merge, The collision will send gravitational waves rippling across the universe powerful enough to be detected by future observatories. Humanity may one day measure that signal as proof of this system's ultimate fate. In a broader sense, the discovery forced cosmologists to rethink how galaxies and black holes co-evolve. For decades, the prevailing idea was that galaxies form first, and their central black holes grow inside them. But the infinity galaxy suggests the opposite may also happen. A black hole can form first and then shape the galaxies around it. Its gravity can organize surrounding gas into new structures, seeding the formation of stars and spiral arms later. The cosmic order may be far more intertwined than previously believed. Every observation added another layer to the puzzle. The black hole's feeding rate implied it was still in an early growth phase. In a few 100 million years, it could reach 10 million solar masses, matching its older siblings in the galaxy cores. That means we might be watching the early stages of a future triple merger event. The resulting black hole could exceed 20 million solar masses, releasing more energy and gravitational waves than any event since the early universe. The entire system is like a cosmic clock, ticking toward a spectacular finale that will not occur for eons but is already written in motion. Yet the emotional impact of the discovery reached beyond equations. For the scientists who first saw that figure 8 shape on their screens, it was a reminder that the universe still holds surprises capable of rewriting everything we think we know. Each pixel of Webb's image represented a photon that had traveled for billions of years, just to deliver a message that the cosmos still experiments with its own laws. The infinity shape itself seems symbolic, a visual echo of endless creation and destruction repeating forever. Some skeptics still question whether the evidence proves direct collapse beyond doubt. Alternative models exist, though none fit all observations as neatly. Some suggest a hidden dwarf galaxy could lurk behind the bridge unseen, but deep field imaging shows no trace. Others argue the turbulence could mask an ejected black hole's motion, but the velocity match is too precise. For now, the simplest explanation remains that the black hole was born where it sits. As data continue to flow in, each new observation strengthens the case. Infrared variability studies show periodic flickers consistent with accretion instabilities in a young black hole. Radiopolarization reveals jet alignment with the gas bridge, implying interaction between the newborn black hole's outflows and its environment. Even the distribution of nearby star formations supports the idea that the central region remains too turbulent for stars, but calm enough at the edges for clusters to form. The system is a microcosm of cosmic balance chaos in the middle creation at the borders. The discovery has inspired new telescope proposals. Scientists plan to use next-generation instruments to hunt for other galaxies showing the same signature, 2 cores, a connecting gas bridge, and a bright ionized region in between. If similar systems are found, it will confirm that direct collapse is not a rare fluke, but a common natural process. Webb's sensitivity may reveal dozens more candidates in coming years. Each one will help refine our understanding of how gravity, turbulence, and radiation conspire to build the universe's most mysterious objects. From a philosophical perspective, the infinity galaxy shows that even in the spaces between destruction, something new can arise. 2 galaxies collided, tearing themselves apart, yet in their death throes they created a new cosmic engine that may one day anchor another galaxy. The story becomes a metaphor written in light across the sky creation, born from collision, order from chaos, infinity from ruin. As the weeks passed, the scientific community responded with a mixture of fascination and disbelief. Conferences filled with debates over what the infinity galaxy meant. Some teams proposed alternative explanations, hoping to preserve older theories, while others embraced the discovery as a long-awaited breakthrough. Papers appeared in every major journal re-examining previous data from Webb to see if other collisions might hide similar signatures. The term infinity-type system entered the language of astrophysics, referring to any double-core merger bridged by ionized gas with a central energy source. Meanwhile, Van Dam and Bremer continued to refine their analysis. They re-examined archival data from Hubble and Spitzer telescopes taken before Webb was launched. Those older images showed faint traces of the two galaxies approaching each other long before the collision became visible in Webb's infrared vision. By comparing positions, they reconstructed the timeline. The impact had begun roughly 500 million years earlier. During that time, the central bridge thickened and brightened, until it reached the density that allowed direct collapse. The sequence proved the event was not instantaneous, but the final collapse itself had been abrupt once the critical threshold was reached. That threshold fascinated theorists. What exact combination of density, temperature, and turbulence made the difference between forming stars and forming a black hole? Simulations indicated that once the ratio of turbulent velocity to sound speed exceeded about 8, fragmentation stopped entirely. In the infinity galaxy, that ratio measured between 5 and 10 across the collision zone, meaning conditions were ideal. If the number had been lower, countless stars would have formed instead of one colossal black hole. Nature had balanced on a razor's edge between two different universes, one filled with new suns, the other with a single abyss. Observations also revealed that the gas bridge was slowly thinning as the black hole consumed its surroundings. Over the next few 100 million years, it would drain much of the remaining hydrogen, leaving behind two smaller galaxies, orbiting a shared center dominated by the newborn black hole. In time, gravity would draw them fully together, creating a single massive elliptical galaxy with three central black holes spiraling toward union. The infinity galaxy was not static. It was a story unfolding across eons, each stage rewriting another line of cosmic history. For the public, the discovery carried a kind of poetry. The image of two galaxies colliding to create something new captured imaginations far beyond scientific circles. Artists rendered the infinity shape in light installations. Writers compared it to mythic tales of creation emerging from chaos. Even those who knew nothing about physics could feel the meaning. In destruction, the universe was creating again. But for scientists, the deeper message was about time. Until Webb, humanity's understanding of the early cosmos was limited to faint smudges of light, barely visible through older instruments. Webb's infrared eyes could pierce the dust and see epochs previously hidden. The infinity galaxy showed not just what happened billions of years ago, but how similar processes might still occur. The universe did not finish building itself in the first billion years. It continues experimenting even now. The physics behind that experiment forced revisions in cosmological models. Simulations of galaxy evolution must now include turbulence-driven direct collapse as a possible pathway. That means the number of heavy seeds in the universe may be far greater than predicted. If true, the population of intermediate mass black holes could fill the cosmic web like hidden nodes, linking galaxies through gravity. Detecting them will require new techniques, since many may sit in intergalactic bridges too faint for current telescopes. Future missions like the Nancy Grace Roman Telescope and the proposed LISA Gravitational Wave Observatory are already being designed with this in mind in their private notes. Van Dam and Bremer described moments of quiet, awe while analyzing the data. They wrote about long nights staring at spectral lines, realizing that each pixel on their screens was light emitted billions of years before Earth even existed. To them, the infinity galaxy was more than a scientific object. It was a time capsule from a universe still young and wild. They often imagined what it would have looked like up close. Two vast disks of stars colliding silently in the vacuum, shock waves rippling through space, a glowing bridge forming between them until gravity itself tore open a hole in reality. As more data accumulated, another pattern emerged. The alignment of the three black holes suggested that the collision occurred along nearly the same plane, meaning their eventual merger would likely produce one of the strongest gravitational wave events in the local universe. Even though that final collision lies billions of years in the future, simulations can predict its signature. One day, far from now, space itself will ripple with the echo of this cosmic dance, carrying the faint tremor of the moment when three ancient monsters become one. The philosophical implications were just as profound. Humanity has long assumed that creation requires stability, that order emerges from calm conditions. The infinity galaxy proved the opposite. It showed that even the most violent destruction can give birth to structure, that chaos can be a form of creation. It reminded scientists that the universe is not a static machine following simple rules, but a living system capable of surprises. Every time instruments improve, nature reveals another layer of its imagination. In classrooms, the story became a favorite example of how science progresses. Teachers explained to students how one unexpected observation can overturn decades of theory. The lesson was not that earlier scientists were wrong, but that the universe is always more complex than our models. Direct collapse had once been dismissed as fantasy, yet there it was, written in light across billions of years. The infinity galaxy transformed from curiosity to cornerstone, reshaping how future generations will study cosmic origins. As for the team, their next goal was to find more examples. They combed through Webb's database searching for other figure-8 structures or twin-core systems with unusual radiation patterns. Within months, they found several candidates, though none as clear as the first. Each potential discovery added momentum to the idea that the universe might be filled with hidden infinities waiting to be found. The more scientists looked, the more they realized how interconnected everything is. The growth of black holes affects star formation, which affects galaxy shape, which in turn affects how matter distributes through the cosmos. In that sense, the birth of a single black hole between two galaxies is not an isolated event, but part of the ongoing architecture of existence. The universe builds itself through feedback loops, destruction feeding creation, energy cycling endlessly. At conferences, Van Damme often closed his talks with a simple reflection. He would show the Webb image of the infinity galaxy and say that this is the universe's handwriting, an infinity symbol drawn not on paper but in light and gravity, a reminder that even in the coldest emptiness, creation never stops. The infinity galaxy became more than a scientific term. It turned into a symbol of how discovery reshapes understanding. For the first time, astronomers had tangible proof that the universe still experiments with creation, that it can invent new pathways to the same cosmic destinations. Before Webb, the story of black hole formation was simple. Stars lived, died, and collapsed. After Webb, that story fractured into something richer. The cosmos no longer needed time or order to create. It could skip steps entirely, building giants in places no theory had predicted. Each observation session brought new details. Webb's infrared instruments tracked fluctuations in brightness that hinted at rapid changes in the accretion flow. It was as if the black hole's feeding was pulsing, sometimes dimming slightly before flaring up again. These oscillations suggested unstable flows of gas spiraling inward, similar to heartbeat patterns seen in smaller black holes closer to home. It gave researchers a living view of a black hole still settling into existence, like an infant star flickering before reaching balance. Van Damme often said the infinity galaxy was the universe caught in the act of breaking its own rules. His team used every available instrument to test that claim. The European Southern Observatory confirmed faint gravitational interactions between the two galaxies' stellar populations, showing that their orbits were still distorted from the impact. The Very Large Array mapped faint radio jets streaming from the black hole's poles, proof that its magnetic field had already stabilized enough to accelerate charged particles to near light speed. The Chandra telescope detected hard X-rays tracing the edge of the accretion disk, revealing temperatures of tens of millions of degrees. Everything pointed toward an object young, violent, and hungry. Still, questions lingered. How much of the original gas bridge would the black hole consume before the rest dispersed into space? Would it grow into a monster rivaling the central black holes or fade into dormancy once its food ran out? The models showed multiple possibilities. In some scenarios, the black hole would consume the bridge entirely and anchor a new merged galaxy around itself. In others, gravitational interactions would fling it away, sending it drifting through intergalactic space as a rogue. The next 100 million years would decide its fate. For now, it remained suspended between creation and isolation, glowing faintly across billions of light years. To the scientists, even its impermanence carried meaning. The infinity galaxy showed that nothing in the universe is truly separate. Galaxies collide, merge, and reshape themselves. Every end folds into a new beginning. The black hole between them is not an intruder but a mediator, converting chaos into balance. The more researchers learned, the more the discovery felt like a message written in physics. Even destruction can be an act of creation. For the world watching from Earth, the story carried another message. Webb's mission had often been described as humanity's new eyes on the cosmos. The Infinity Galaxy proved those eyes could not only look farther, but see differently. They revealed forms of order hidden within cosmic violence. When images of the galaxy were released to the public, millions were captivated by the bright green bridge, the twin red cores, and the quiet void where the black hole hid. The image became one of the defining visuals of Webb's early years, an emblem of how far human curiosity could reach. As data continued to arrive, models of the early universe began to shift. Astrophysicists incorporated turbulence-driven direct collapse into cosmological simulations, and the results aligned more closely with Webb's discoveries of massive black holes in ancient galaxies. Suddenly, the impossible timeline of billion solar mass quasars, less than a billion years after the Big Bang, no longer seemed impossible. Heavy seeds created through direct collapse could explain them all. The Infinity Galaxy, though far younger, acted as proof that the mechanism was real. Theorists began tracing other potential effects. If direct collapse can occur during galaxy collisions, then similar events might trigger bursts of gravitational waves even before the resulting black holes merge. Detecting those subtle ripples could become a new way to identify heavy seed formation. Missions like LISA would one day listen for them, turning space into a giant cosmic seismograph capable of hearing creation itself. The Infinity Galaxy had become the prototype for that search. In the years following the discovery, the research community continued to refine their understanding of how turbulence, radiation, and gravity combine to shape cosmic evolution. Each simulation became more detailed, incorporating magnetic fields, feedback loops, and relativistic effects. The more precise the models grew, the more they confirmed what the observations already hinted. The universe prefers efficiency. When it can take a shortcut, it does. Direct collapse is one of those shortcuts, an elegant solution to the problem of time. For Van Dam, that realization carried emotional weight. He often said the black hole was not just a scientific object, but a mirror for human curiosity. Like the gas collapsing under pressure, knowledge itself compresses under the weight of mystery until it bursts into revelation. Each discovery, he believed, is a kind of collapse, a moment when understanding condenses into clarity. The Infinity Galaxy was one of those moments for the entire field of astronomy. As new instruments prepared for launch, Webb's image remained a reminder of how young our understanding still is. Somewhere in the vastness, more collisions are happening right now, bridges of gas stretching between dying galaxies, turbulence building toward the next cosmic collapse. Each one might already host another newborn black hole, invisible for now but waiting to be seen. The Infinity Galaxy is just the first we've caught in the act, and so the universe continues its quiet experiment. Two galaxies collide, gas compresses, gravity overwhelms, and light bends around a newborn horizon. The bridge between them glows green for a time, a fleeting signature of creation, before fading into darkness. Long after the galaxies merge, the black hole remains, a reminder that even where everything seems lost, something new can still begin. Over time, the Infinity Galaxy became a benchmark against which new discoveries were measured. Each time Webb or another observatory detected an unusual structure or unexplained radiation signature, scientists compared it to the infinity profile. It became the standard example of how nature could create heavy seeds outside normal galactic centers. Graduate students wrote theses about its dynamics. Computer models were refined using its measurements. Its story began appearing not just in journals but in documentaries, lectures, and books about cosmic evolution. What started as a quiet anomaly turned into one of the defining finds of the modern age. Even with all the progress, one question still haunted researchers. What exactly triggered the moment of collapse? The data showed turbulence, density, and heat, but not the final push. Some suspected magnetic reconnection events compressed the gas at the center just enough to trigger relativistic instability. Others proposed that colliding shock fronts from both galaxies produced overlapping pressure waves that forced the gas inward faster than it could respond. Whatever the mechanism, the evidence suggested the transition from turbulent chaos to gravitational collapse happened suddenly, within less than 1,000 years. On cosmic scales, that is a heartbeat. Understanding that moment could reveal much more than how black holes form. It could also explain how galaxies regulate themselves. If collisions can create black holes that quickly, then perhaps such events are one of the ways the universe balances its own structure. Black holes are not just endpoints, but stabilizers. They absorb excess energy, compress scattered matter, and anchor new systems. They are cosmic regulators as much as destroyers. The Infinity Galaxy reminded scientists that balance in the universe often comes through extremes. Years after the discovery, the combined data from Webb, Chandra, and the Very Large Array continued to show subtle changes in the region. The hydrogen bridge was thinning, its light fading as gas continued to fall inward. The twin galaxy cores were drifting closer, pulled by their shared gravity. The black hole at the center remained active, though its feeding rate had started to decline. Astronomers predicted it would enter a quieter phase within the next few 100 million years. Eventually, all three black holes would merge into one, creating a single powerful core for a new galaxy. In that distant future, observers elsewhere in the universe might see the event as a flash of X-rays and gravitational waves announcing the union of three ancient giants. For now, it exists as a frozen moment in time, captured by light that left billions of years ago. When that light began its journey, Earth's continents were still shifting into familiar shapes. When it finally reached Webb's mirrors, humanity was ready to understand what it meant. The gap between those two moments is filled with silence, but in that silence the universe whispered a new chapter of its story. The discovery also influenced how scientists thought about the boundaries between theory and observation. Before Webb, direct collapse had been purely theoretical, an elegant solution waiting for evidence. The Infinity Galaxy turned it into reality. Theories are fragile until the universe confirms them. Once confirmed, they become bridges to deeper understanding. That transformation from speculation to evidence is what gives science its quiet power. For younger astronomers entering the field, the Infinity Galaxy represented hope that major discoveries were still possible. It reminded them that even in an era of advanced simulations and precise models, surprises can still appear in the data. The universe is vast enough to defy prediction. There will always be phenomena waiting to overturn assumptions. The Infinity Galaxy is proof that the cosmos still holds mysteries large enough to humble us. Philosophers and poets drew meaning from it too. They saw in its image a reflection of the human condition. Two entities colliding, destroying parts of themselves, yet together creating something entirely new. The symbol of infinity glowing between them seemed to speak of continuity, of how existence folds back upon itself endlessly. The black hole at the center became a metaphor for transformation, where loss and creation become indistinguishable. Van Damme, reflecting on the years of study, often said that what moved him most was not the data, but the idea that the laws of nature could reinvent themselves. The discovery suggested that the universe is not finished evolving, that its creativity is ongoing. He believed that the cosmos, in its endless experimentation, mirrors the same curiosity that drives human minds. Both are restless, always reaching for the next possibility. Eventually, more systems similar to the Infinity Galaxy began to appear in Webb's expanding catalog. Some were faint and distant, others closer and easier to study. Each one strengthened the case that direct collapse is a recurring process rather than an ancient relic. Patterns began to emerge. Wherever galaxies collided head-on and turbulence dominated, traces of intense radiation appeared between them. Each case added another data point to the growing understanding that black holes may be the universe's preferred tool for recycling matter and energy. In the end, the Infinity Galaxy became more than a discovery. It became a perspective shift. It taught humanity that the universe is not static, but endlessly adaptive. It reminded us that even our most trusted explanations are temporary. Science does not move by certainties, but by corrections, and every correction brings us closer to truth. As for the light that revealed it, that light will continue traveling long after Webb's mirrors have cooled, and its mission has ended. Somewhere in the distant future, perhaps another civilization will catch that same light, and wonder what kind of beings first studied it. They will find records of humans pointing telescopes toward the void, trying to understand the shapes drawn in the dark. They will see the figure 8 and read it as we did, a symbol of connection and continuity written in galaxies. When we look at that glowing bridge, we are seeing the universe teaching itself. Two galaxies collide, energy reshapes matter, and from the chaos emerges understanding. The black hole born between them is not just a product of gravity, but of the universe's own desire to evolve. Its hunger is the same as ours, the same force that drives life to explore and mind to question. In that sense, the Infinity Galaxy is not distant at all. It reflects what we are made of: curiosity compressed into being, matter collapsing into awareness, infinity expressed through light. And so, the story ends where it began, between two dying galaxies, in a bridge of light where something impossible was born. A black hole 1,000,000 times the mass of our sun, floating in the emptiness between worlds, rewriting what we thought we knew about time, growth, and creation. The cosmos, it seems, is still inventing itself, and we are lucky enough to witness the moment it happens.